Welcome to the Transitional AI seminar series. Today we have TJ presenting for us. TJ just recently finished his master's at UNSW. So he's presenting a paper that he worked on in one of his final projects using unsupervised learning frameworks for identifying minerals on Mars. And I'll let TJ take over and take you through this presentation.
Thank you. So hopefully if Professor Chandra has some grace, this will be my last presentation and last thing at uni. So hopefully I'm almost there. So the idea of identifying minerals on Mars using remote sensing data was Professor Chandra's idea. But my contribution to it was the introduction of the self-organized map model as the learning algorithm to identify where those minerals are, which is what I'll take you through today. To explain our kind of thought process as to where we landed, evidently there's no data really for Mars as to minerals that are there, so we can't use a supervised model. We're in an unsupervised framework due to that limitation. But we do have plenty of hyperspectral data. But the problem with hyperspectral data is it's large, it's complex, it's noisy, and it's very difficult to use due to those reasons. So when we were researching this, we came across this approach, which is called summary parameters. And what people in this space do is they take the hyperspectral data, convert it into these summary parameters, which don't really lose any information in terms of your ability to identify a mineral, but it compresses the hyperspectral data down a bit, which makes it nicer to work with. So we kind of latched onto that idea and thought, well, yep, we can process the hyperspectral data into these summary parameters and then cluster that to identify our minerals. The additional step that we've taken is we found a very small library of known minerals on Mars and the hyperspectral signature of those minerals, which means that even though we were in an unsupervised framework, we were able to link kind of these two to also be able to label our clusters that we identified, even though it's unsupervised. So to give an idea of how these summary parameters work, you can see in the background here the raw hyperspectral data, which is very noisy, difficult to work with. In some places, there's no data. And what we want to extract from that is information that's important to us. So as an example, if I wanted to identify the minerals alunite and gypsum, one of the key things that would be looked for is if there's an absorption feature at 1,750 nanometers. And if there is, then that's an indicator that those minerals are there, and that's unique to those minerals, right? So this is the particular parameter that is used to test for that absorption feature. And basically what it's doing is it's zooming on this little part of the hyperspectral data, which is this. And it's got these two anchor points here, which are those 2 points there. And at the 1,750 nanometer part, it's testing to see if there's a dip there, which in this case, you can clearly see that there is. But you can also see some of the dangers with using hyperspectral data, because in this instance here, we've got kind of this rogue data point. So the way these formulas work is a bit complex, where you actually take the median around those points. So in this particular case, it's the median three nanometer kind of spacing around here, which would give us this point. But you can see some of the dangers in using this data raw, but these types of parameters kind of overcome that, and they preserve what we want to get from here to identify a mineral. So if I actually apply just that summary parameter to the CRISM library, which is the library of these minerals on Mars, you can see that that summary parameter was really only responsive to alunite and gypsum, which was the two minerals we were looking to detect. And all of the others basically didn't have an indication at that particular point. So basically, what we wanted to do now was to build up a set of summary parameters to test for all of the minerals to be able to do our clustering. So to do that, this is reproduced from other research by Viviano. And basically what this research has done is identified all of these summary parameters that you can kind of use to identify these known minerals on Mars. And in addition to that, you can use even more summary parameters to get these color overlays, which I'll use later so you can visually see minerals on the Martian surface. So if we have a look at, say, some of this, for say your iron oxide and silicates, you can see that they're particularly responsive to these summary parameters, but not the rest. Whereas with sulfates, they're responsive to these summary parameters, but not the first ones. All right, so you can see how you can use the outputs of these summary parameters to cluster mineral groups and also minerals. But you can also see there's a bit of a hierarchy to this data as well, because you know that if the first three parameters are 0, then you kind of know, well, it's not that, it's got to be one of these other things. So not only did we want to identify and cluster those minerals, we also wanted to preserve that hierarchy that's inherent in the data. So the way we kind of went about doing this was the self-organized map approach. So the way to think about a self-organized map is it's basically a cluster, such as what you get from k-means, right? But instead of just having random clusters everywhere, it will organize those clusters into a 2D grid. So not only do you get your cluster, but you get an organized grid of those 2D clusters. And one of the unique things about that is you see the topology. But secondly, if I want to represent what that cluster means, a SOM model will give me a weight for each of those individual clusters, so I can automatically represent that data that's underneath. And that weight is also partially determined by the neurons around it, unlike k-means where it's all just belonging to that cluster. So an alternative way to think about a SOM model versus other unsupervised techniques is k-means is basically a disorganized jigsaw where each of the jigsaw pieces is a cluster, but the clusters are just spread everywhere. In the case of a SOM, you have the same clusters pretty much, except they're organized into this coherent pattern. And it's that 2D grid that we're buying with the SOM model that sets it apart from other approaches. In terms of the learning process as to how a SOM model learns, we have that 2D grid. These are all of our clusters. And when it goes through the learning process, if I have a instance, it will identify which cluster that instance belongs to, what's best matching unit. Then what it will do is, for that best matching unit, but also other units around it, it will apply an update of a, and that scale, it's a gradient kind of update, a scaled gradient update to draw in other neurons around it closer to that point. It doesn't actually shift the neurons itself, it just changes their weights. Yeah. So what we kind of want is, at the start, is a very violent updating of this grid, and then towards the end, we get a refinement of it. Now, how we go about doing that, get back one. So I'll visually explain this mass in a moment. I'll just take you through it as anyway. So it starts with, we have a decay function, and you can kind of use whatever decay function you want. We just used an exponential decay function in that case. And the purpose of that decay function is to take our initial radius update and learning rate, which I'll explain later, from an initial value down to some other value as training goes on. Those three parameters feed into this neighborhood function, which is just basically a Gaussian distribution, which is what gives you that gradient, that red gradient I showed before. So you've got your radius update, your learning rate, and then we've got this distance. So how much an update each neuron gets depends on how far it is away from other neurons, and that's just based on the coordinates of that neuron compared to the best matching unit. And the weight update itself is just the difference between what the existing weight is, what the instance we're fed in, multiplied by this weighting here, gives you your new weight. And that's basically all it is, what the learning process is. So graphically, if I take the radius update as an example, you can see our initial value here of 25. We chose 25 because we were using 50 by 50 grids. So 25 means at the start, pretty much half the grid is getting updated on each iteration. And that decay function sets in to take it below 1 at about the 750th learning iteration. So the reason why we chose this particular form was to set this so it only dropped below 1 after about 75% of the learning, and the remaining 25% is just polishing off individual neurons. So we shift from topological structure down to individual clustering kind of polishing. And if I show the same thing in a different way, if we have a case where our best matching unit is at position 1010, which is here, then you see at the start, you have that radius of 25, which limits where the update's applied to. And then you have that neighborhood function that's applying a different intensity the further you are away from that best matching unit. And at the start, all of those neurons get updated. But as you progress further through training, it will then focus down onto more of a local neighborhood structure. We have a few interesting steps in terms of how we actually went from the raw data to training the model. We actually found quite a few errors with NASA's own calculations of these summary parameters. So we actually went back to the raw hyperspectral data, corrected some of those summary parameters, recalculated them ourselves. We clip any summary parameters that are below 0.20 because inherently you're testing for a depth, and that's got to be positive. The formulas don't specify that it's bound by 0, but it is. So we clip any negative values to 0, then normalize to 0 to 1. And then we did this step, step 3. This step was quite important. So once we had those summary parameters for each pixel, we then applied k-means to that data. And the reason why we applied k-means, but we did it in a way where the smallest cluster had 10% of the pixels. So we kept expanding the number of clusters until the smallest cluster had less than 10% of all the pixels in the image. And the reason why we did that is in some cases or in some regions, you can have 90% of that region's all the same memory. It's just the same spectra in each pixel, one after the other. And if we just randomly sampled from that raw data, the SOM model wouldn't be learning anything. It's just seeing the same thing over and over and over again. But by doing it this way, we can isolate all the different types of spectra up front. And then from those buckets, we sample equally from each bucket, which means that the smallest bucket is getting proportionally more instances fed into the model than the larger bucket, but it ensures the diversity of what the SOM model is learning. We then have to sequentially train the SOM model, which means even though we select n instances from that process, each instance is fed one at a time into the model, which actually makes it really slow because you can't do batch processing, you can't do parallel processing. It's got to be done sequentially. And then we repeat those steps a certain number of times. In our cases, we repeated that 1,000 times. Each batch, we had 5,000 instances that we trained in that particular batch. So I'll now show you for a particular target region, it was known that low calcium pyroxene, I think is how it's pronounced, is in that region. And the initial 2D grid output of our SOM model looked like this for this particular mineral. So each one of these little squares here is one of those neurons. So you can think about each one of those little squares as like an individual kind of k-means cluster. But you can see how the SOM model has organized those clusters in such a way that clusters representing low calcium pyroxene are all kind of clustered in this corner up here. So what we're looking at here is the correlation of each neuron to that mineral in the library, and it's telling us that this is the zone where that's been put. So a couple of things from this. When you're using a k-means model, you have to select your height parameters as to how many clusters you want to form, and that's a sensitive thing. In this case, you can quite clearly see we've over-dimensionalized the SOM for this particular mineral. Like there's 100 clusters assigned to it up here where we only needed 1 or 2. But it also shows that the SOM model is particularly robust to particularly over-dimensioning, because if we do over-dimension it, then all it's going to do is form a cluster of a cluster. And we can visually see that and work around it. But when we're initially scanning a target region, we don't know how many clusters we need. But the SOM model kind of protects you by letting you over-dimensionalize it and then backtrack from there and visually see what's going on. The other benefit to this is one of the complications of finding minerals on Mars is many areas have multiple minerals in the same location. So you have mixed spectra. And that makes it difficult to identify a particular mineral. But what we can do in this case is we can find the really high confident regions where the mineral is very pure, look at that first, and then expand out to more speculative zones if we want to. So if we take that exact approach, we have a false view of the image on Mars. And we have these little red dots here, and those little red dots are the actual pixels that have been identified as being this particular mineral in this location. And the white box kind of delineates roughly the broad zone that those red pixels are in. And the yellow crosshair is where that mineral from other research was previously identified as existing. So we can see that our model identified the region pretty much spot on. It even got the exact pixel that was previously identified from other research. If, however, we switch to one of these color overlays, you can clearly see where the mineral is in this location by the aqua zones. But you can see how our strategy of starting with high confidence regions has identified the high confidence zone, but there's also other zones that we wanted to ideally get here as well. So if you remember on that 2D grid before, there was about 100 clusters within that cluster. If I now go from the top 5 to the top 50, so taking half of those clusters, we then see we basically then kind of identify the whole zone where this mineral's located. So that's an example of how the SOM model organized the individual clusters into an overall map that maintained a structure and that hierarchy, and how we can use that to identify high confidence regions and then expand it to lower confidence regions. So this next one ventures into uncharted territory where we're actually identifying a mineral that wasn't known to exist there, and how we were able to use the SOM model to identify that mineral. So in this particular case, we're not looking at the correlation to any particular mineral. What we're looking at is the number of times or how many instances are clustered under each neuron. So you can see for this particular neuron here, there's about 350 pixels clustered underneath it. But then we have ones like the blue ones where there's between like 0 or 50, so only a handful of pixels. Now, if I use k-means, all of this data would be scattered. But because it's organized, I can see this very distinct region up here where it's really telling me, look, there's a mineral up here that's unique, right? Because there's not many hits of it, but all of these neurons or all of these clusters are related. And therefore you need to look at what's going on up here.
Yeah.
So when we went through the library to see what kind of mineral correlated with that zone, what we found was sodium carbonate was the mineral that was responding to those neurons up there. The interesting thing is this other mineral, iron olivine, was pretty much everywhere in this image. So that's one of the situations where 90% of the pixels are all the same thing over and over and over again. But because of that learning strategy of pre-isolating clusters, we're able to get this learning. But sodium carbonate is quite highly correlated to iron olivine. Many of the summary parameters are the same apart from 1 or 2. which is why we get this broad zone of correlation, because that's your iron or vein. But then you get this bit more separation, which is your sodium carbonate. Once again, you can see how the SOM model separated all of that data. And once again, you can see the benefit of going from high confidence to low confidence regions when you end up in situations like this. So now we will look at the false view of that area. If I didn't do a false view and I showed you that iron or vein, basically will be iron or vein, aside from those very distinct. So that's the overlay that's designed to check to detect sodium carbonate, and you can see it got it spot on. That's a very isolated mineral in that zone, and we were able to identify that because we had that topology overview to guide us. So within our paper, we have other examples of identifying minerals where it's been previously located. We also show how the SOM model organizes entire mineral groups, not just individual minerals. And we also show that the SOM model has a preference for kind of projecting minerals to the edges of the SOM grid, and everything in the middle is kind of just junk. So that's an important observation to guide for mineral detection, to look around the edges and corners in particular. But it's very interesting how when you have mineral groups that are even slightly negatively correlated with each other, the SOM model will really separate them and push them well apart. So in terms of the clustering performance of the SOM model compared to k-means, firstly, they're not comparable models because k-means doesn't give you that topology. And secondly, I have a lot of hyperparameter options I can choose with the SOM model. For example, we chose to use 5,000 instances per training batch and do 1,000 training batches. But I could have quite easily chosen 1,000 instances per batch and only done 500 training instances. I got complete control over that, and that changes how long it would take to run this model. So even because of that, you can't directly compare. But if we go through a few metrics, this is looking at that previous mineral, sodium carbonate, to see how well the two models did. Because of the time it takes to run a SOM model, we only did 2 runs of various SOM sizes. But we did 30 iterations of k-means to get the confidence interval, which you can see here. So what you can see is the blue line is the mean number of instances that k-means clustered. So it was around about that, say, 240 pixels, which represented that mineral. You can see the SOM model stuck very closely to that. So despite changing the number of neurons we were using, it consistently generated the same output, whereas k-means was quite wild in terms of what it clustered, especially for a smaller number of clusters. So the key point there is the SOM model seemed to be a bit more resilient and stable no matter what we chose. In terms of clustering performance, we used mean weighted distance to test how far each instance was away from either the center of the k-means clusters, or in the case of the SOM model, the neuron weight. And we see that both SOM models were well below that of the confidence interval for k-means, indicating that the SOM generated a lot tighter clusters, which is good. And the reason why it generated much tighter clusters is it seems that topology guided the SOM model to allocate more resources to unique spectra. Probably because those areas were getting hit more often, and you're getting that organization around those clusters. So you see, for example, when we used 2,000 clusters for k-means and the SOM model was allocating about, say, 75 clusters to sodium carbonate, whereas k-means was only allocating, I don't know, about 30, say 35 or so, which therefore explains why you're getting the better clustering. The downside to a SOM model is the execution time can be horrendous. So if we did the 50-50 model that we did, it's taking up to like 7 hours. But the interesting thing is the execution time is not consistent. So for example, a smaller model that actually took me 9, almost 10 hours to do. And I think that's got to do with the fact that you have that sequential updating one after the other. So depending on which CPU you get allocated or whatever, you tend to get that variance. I don't know why. but it takes a long time. But if you're going to Mars, it takes like 2.5 years to get there. So, you've got plenty of time.
Yeah.
All right, so the key findings of this research, we can use those summary products to reduce the dimensionality of hyperspectral data without necessarily losing important information. We would recommend in the future automating the generation of summary products because of those errors we found with NASA's own data and everything. It's a task that shouldn't be done manually. We've shown that unsupervised algorithms can be used to cluster those summary products and identify minerals. And although the SOM model is very expensive to run, preserving those topological relationships is not only interesting and intuitive, it can help guide you in identifying high confidence regions and also unique minerals in certain locations. And lastly, if you're not satisfied or confident in these results, NASA's offering one-way tickets to Mars. You can go there and check it out for yourself. My mobile number might change in that time, but you can go there and check it out. Otherwise, that's all. Thank you, everyone, and thank you for Professor Chandra. Next.
Thank you.
Do you have any questions?
Yeah, I do.
Go for
Please,
it.
can you go to the steps?
On
The
the
steps,
steps?
yeah. Yeah. So, my first question is, you talked about K-means clustering. Something is not clear with me. I understand that some by itself can create clusters based on the 2D by similarity or topology can be able to assign the clusters, all right?
Yep.
But K-means you automatically need to assign which clusters, number of clusters to K-means.
Yep.
So what amount of clusters did you do? Then second question, random sampling. Did you do random sampling which decimals of sampling? Third question, the decay weights. I was interested in the decay weight aspects. You did an exponential part. Do you think if we apply the logarithm aspect, it might something change? Because exponential is like going the other way. Do you feel like if we try logarithm, something interesting might come out?
Okay,
Because
so,
sometimes logarithm might be a little bit more.
so I'll try and remember the 4 questions. So step 1 was how do we select the number of k-means clusters in step 3?
Yes.
So that was an iterative process where I set a target that the smallest cluster needed to contain less than 10% of the instances.
Okay.
So if it didn't, I just
Then
increased the
maybe
number
of
of
it.
clusters
Okay.
until it did. That was question number 1. So question number 2 was, did I sample with replacement?
Replacement or
Yeah. So gets replaced and
you get replaced.
gets replaced. So from step 3, the spectra that's in those clusters doesn't change. Right?
Okay.
They're assigned to that cluster. And in step 4, we're sampling a certain amount of instances from each of those clusters equally, but randomly. So it may be the case that in that final cluster, you might only have, say, 2,300 instances, and each of those instances may be fed into the SOM model 4 or 5 times for learning throughout that entire process. So once they're being fed in, they do get replaced again. And that's not necessarily a bad thing that the same data comes in, because remember, a lot of this is just getting that topological organization sorted out. So once you just position all of those neurons in a way that makes sense, it kind of doesn't matter which spectra you use to do that. You just want to see it get hit quite a few times to get that organization.
So in other words, they are almost like the same thing. Even if I do it without replacement, it won't change anything.
Yeah, but we are because we're feeding it one at a time, each time we feed an instance into the model, it's likely to be in a different area of that SOM map. So if I take an instance from cluster 1 and an instance from cluster 10 here, they're likely to be updating 2 different areas of the SOM neuron.
Yeah, I understand. Why I was asking, because I was checking if every other instance has a core chance of still being selected in the sample, in the cases. That was why I asked if
Okay.
it was with or without replacement.
I might say it differently as to why it failed if I didn't do it that way.
Okay.
Okay, because if I had 90% of instances in a area that was all the same, or roughly the same mineral, and I just randomly sample blindly from that, then there's a 90% chance that what I sample now is going to be the same as what I sampled before.
Yeah.
And what that does is it forces the SOM model just all converges to one kind of spectrum.
Okay.
And we don't want that. We want to have that, preserve that diversity.
Okay.
Like it's going to have enough clusters to learn that 90%.
Yeah, it makes sense.
Yeah, so we needed to break it up like that. The second one was the log, the fourth one was the log thing. So that's
Yeah, the decay.
uh,
I think I have one more last question. Yeah, the decay aspect.
so you would be wanting
Yeah.
to replace this with
Exponential.
something like that, with something like
Yeah.
that.
What do you think?
I would think you would have a danger of getting too much topological organization and not enough one down
So
here.
okay.
Maybe if you had some sort of curve that went like that.
That's more like okay.
Maybe like a sine.
Like goes in X format.
Yeah. You just need to get that balance between having a very violent updating at the start, but then once you've had that violent updating, let it settle down and focus. Whereas if you have too much going on up here, then you're just going to get the whole thing just shifting around unnecessarily. Like once it's shifted once, you want it to kind of settle and maintain that pattern,
Okay.
not reorganize it all over again.
Yeah.
Basically adaptive momentum, right? Something like
Yeah,
adaptive momentum.
adaptive. Yeah.
So from a large
Yeah.
search space to a smaller search space.
Yeah.
So all of those neurons are set with a random weight to begin with.
Yeah.
So all you're doing is basically just trying to organize those random weights and make them not random at the start.
Okay.
Once you've achieved that, then you don't want to go there again. You want to
Yeah,
be
yeah.
down this end.
Just want to go down.
Yep.
Okay, the last one on the two plots of your diagram. Sorry, I'm asking too much, but was that interesting stuff?
Have I gone too far?
No, back. This information you said here it was the alunite identification.
Oh no, I think the one you're after, if it's alumni, was that one.
The aim was to identify a mineral. The two
yeah.
of the minerals here.
Okay, so that's the two minerals.
You want to identify, right?
Yeah, they're the ones that we targeted.
Now the first we had the first identification, and then the other one we have to identify is sodium, right?
Sodium carbonate.
So the first identification, was it alunite identified or?
No, that was low calcium pyroxene. Yeah.
Okay, so intention was strictly to identify a mineral, not a specific mineral.
The intention of that location was to find that particular mineral because we've known from previous research that that mineral was there. So that was kind of like a way to kind of ground truth. Are we actually getting the location right?
Okay.
Yeah. The next one was we had known from other examples we've used that we are getting the location right.
Yeah.
Now we've seen a unique pattern here, and we just wanted to know what that mineral was.
Okay.
Yeah.
Okay. Thank you.
That's all right.
I have a question about your data. So the data that you gathered from NASA, it's at a point in time. So you just have a single time instance, or are there multiple time instances of data?
No, it's a single time instance because they're just remote sensing a very specific location
Once.
The risk to that is if you have atmospheric and things like dust storms or whatever, that will create a problem. But they do apply corrections to that data.
I was just wondering whether we could apply it at a different time instance because it would have same minerals there. At a different time state, we'll be able to get the same reflectance on it.
Yeah, fun.
Right, that's all I had.
Okay.
Do you have any questions online or any comments? Do you have any other people on top?
Thanks, Ratnil and TJ for this. Yeah, thanks, TJ, for excellent work. That was an excellent thesis, and I'm really honored that you contributed. I just want to comment more on the code and the data availability. Could you say more about that? And if we want to reproduce this, the GitHub repo and an overview about it would be great.
Sure. Well, firstly, thanks for your patience and time, Professor, in getting this eventually done. So if anyone wants, so the a SOM model is not a library that you can get in Python. So we had to adapt some kind of pre-existing code to get this to work. So if you go into the paper itself, there's a data availability section there where you can go to GitHub to get all the Python code that we used to generate this. That also links into Noodle, Zendo. Yeah, links into that. Not only does it link into it, but I've also put on there the other data sets for the target regions that we've mentioned here. So everything can be replicated from that code and the data that we use. Yeah. All right. Well, hopefully that's
all right. Thank you very much.
Thank you.
Thank you.
All right. Bye-bye. Thanks.
Bye.
Everyone, thank you for joining online.
Yeah.
Cheers.
Cheers. Bye-bye.